Hello and welcome to another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 2, Lesson number 3 on function composition. Function composition is a very important topic, and you are ready for it at this level. The idea is very simple. We're going to be putting together two or more functions all at once to see what their sort of combined effect is. Now, you do this all the time, and in fact, the first exercise is going to help us think about this quite a bit. So let's jump right into it. Exercise number 1, a circular garden with a radius of 15 feet is to be covered with topsoil at a cost of $1.25 per square foot of garden space. Letter A asks us to determine the area of the garden to the nearest foot. All right, so we're going to determine the area of the garden, and of course we all know how to find the area of a circle. The area of a circle is given by pi r squared. So if the radius is 15 feet, then the area of the circle is going to be pi times 15 squared. Because we want this to the nearest square foot, not in terms of pi, which kind of makes sense because we're doing something with it that, is practical, then we would just multiply this all out on our calculator. It's kind of a messy answer. It turns out to be like 706.858, etc. And that ends up being 707 square feet of area. Now that was a function, right? The input was the radius, and the output was the area. The input was the radius, and the output was the area. But letter B now says, using your answer from letter A, calculate the cost of covering the garden with topsoil. Well, we know that the area was 707 square feet, and we're going to multiply that by $1.25 per square feet. Remember how units cancel? And that's going to give us $883.75. So think about this for a second. A radius of 15 went into a function. That function being the area function. And what came out was 707 square feet. Then that 707 square feet went into the cost function, and what came out was $883.75, right? I didn't really care that much about the 707 square feet. What I ultimately really wanted to know was how much it was going to cost me to do this, all right? And that's the idea of composition, an input going into a function, giving us an output, etc. So let's take a look at what that kind of looks like in a diagram. I'm going to have you pause the video now, write down anything you need to, and then we'll move on. Okay, here it goes. I think we'll switch back to blue. So function composition, very simple. We always start with two functions, or more. We could have 3, 4, 5, doesn't matter, but at least two. You have some initial input, and it goes into f of x. Now, what always happens when you have something that goes into a function is something comes out of a function. And the output that comes out of f of x suddenly becomes the input to g of x. And then, just like in our last problem, we get some kind of final output, right? So the idea of function composition is very simple. It's like a row of dominoes knocking each other over, one after another. Okay? Let's take a look at how it looks in symbolic form. All right, so we've got two functions. One of them, the rule is f of x equals x squared minus 5, and the other one, g of x equals 2x plus 3. We want to find values for each of the following. So how in the world do we even interpret this? Well, it's actually not that bad, because g of 1, this thing right inside of here, that's got a value. G of 1 is, 2 times 1 plus 3, so g of 1 is 5. But equals can always be substituted for equals, so f of 5 then is 5 squared minus 5, which is 25 minus 5 is 20. And that's it. F of g of 1 is 20. Notice how I said that. Let me do a little erasing here because this got a little bit busy. I said f of g of 1. So I've got g of 1, which sits inside of f. It is the input to f. Now, it's not that g has to come first and f has to come second. In fact, if you look at this, g of f of 2, it implies we really have to figure out f of 2 first, right? Which would be 2 squared minus 5, which would be 4 minus 5, which is negative 1. I now need to know what g of negative 1 is. That's 2 times negative 1 plus 3. And that's negative 2 plus 3, and that's positive 1. That almost looks like a 1. That probably looks less like a 1. Oh, that's supposed to be a 1. G of 0. We can have that. We can definitely have an input go into a function, give us an output, take that output, put it into a function over and over again. So that's all this is saying. This is saying, all right, well, g of 0, that's going to be 2 times 0 plus 3. It's going to be 0 plus 3, which is 3. And then that goes right back into function g again. Now, I think the concept here is pretty easy. What can get a little bit trickier is another type of notation. Some people call this fog notation, not because it makes you foggy, but literally f of g of negative 2. So we know we've got the two functions. The question is, where does the negative 2 go first? And this is pure convention. The negative 2 goes into this one first. So g of negative 2, 2 times, sorry about that, 2 times negative 2 plus 3. 2 times negative 2 is negative 4, plus 3 is negative 1. So that negative 1 now has to be fed into f. So f of negative 1 is going to be negative 1 squared minus 5. Gives me 1 minus 5. Gives me negative 4. All right. So that's a little bit trickier. The previous notation was pretty easy because, hey, whatever the input is sort of inside first, that's the first function you deal with. Here it's way more questionable, but again, the 3 will go into this f. So f of 3, 3 squared minus 5, 9 minus 5 equals 4. Then 4 gets fed into g. G of 4, 2 times 4 plus 3 gives me an 8 plus 3 gives me 11. And again, we can always compose a function with itself. In fact, there's many situations where that makes sense. So the first thing I'm going to do is put that negative 1 into f. That's going to be negative 1 squared minus 5. 1 minus 5 is negative 4. That negative 4 then gets looped back into f. And we'll get 16 minus 5 and 11. All right. So composition. Input goes into a function, output comes out. That output goes into another function, and a final output comes out. It's not too bad. Pause the video now and write down anything you need to. Okay, clearing out the text. Now, if we can do it with formulas, we can do it with graphs. Keep in mind that the inputs are x values and the outputs are y values. So here in this graph, we've got y equals f of x, and in this graph, y equals g of x. So those are going to be our rules given in graphical form. Let's take a look at g of f of 2. Well, the first thing I have to do is figure out what f of 2 is. In order to do that, I go to the graph of f, I go over to x equals 2, and I find the y value is 3. That means I now need to figure out g of 3. So I go over to this, 1, 2, 3, and I find out that g of 3 is 3. All right, I'm going to erase some of that stuff because I don't want it to throw you off. Let's try f of g of negative 1 and then have you work on the rest of them on your own. So first thing I have to do is figure out g of negative 1. Well, I come in here, here's negative 1, 1, 2, 3, 4, 5. G of negative 1 is negative 5. I now need to figure out f of negative 5, so 1, 2, 3, 4, 5. And it looks like that's going to be negative 1/2. All right, why don't you work on the rest of them on your own? All right, let's go through them. G of 1. All right, well, the first thing I want to know is what's that g of 1 equal to? And it looks like it's equal to 3. Now I want to know what g of 3 is. So 1, 2, 3. And it looks like it's 3. All right, now we go to this notation. Remember, the negative 2 goes into f first. So f of negative 2 is positive 1. G of 1 then is positive 3. Love those 3's in this case. 1, 2, 3 of them so far. All right, here I want to go 0 into g. G of 0 is its y-intercept. Oh, g of 0 is 0. Look at that. Corresponds to this point right here. F of 0 is its y-intercept, and that's 2. Huh. Wow, it looks like we just dealt with f of 0, so now we get to deal with it again. As we just saw, f of 0 was 2, and f of 2 is our favorite 3. Lots of 3's here. All right, so we should be able to do function composition if we're given graphs. Hey, we should be able to do it if we're given a graph and an equation, or a table and a graph. We just need to have two functions such that when I give you the input, you can figure out the output. All right, I'm going to clear all this out. Okay, now, sometimes what we want to do is come up with a formula for composition so that we don't have to do it for each individual x. Now, this can be a little confusing, so let's take a look at it with a pair of linear functions. F of x equals 3x minus 2, g of x equals 5x plus 4. It says determine formulas in simplest y equals ax plus b form for f of g of x. Well, strangely enough, we really don't do anything different than what we were doing. If I put x into g, I get 5x plus 4. Now I'm going to write down something that you haven't seen very much of. I now want to know what f of 5x plus 4 is. Now, what is f of x? Well, the rule says take the input, multiply it by 3, and subtract 2. Take the input, multiply by 3, subtract 2. But now the input isn't x. It's 5x plus 4. So I'm going to take that input, I'm going to multiply it by 3, and I'm going to subtract 2. Doing the distributive property, that would give me 15x plus 12 minus 2, and 15x plus 10. All right, see if you can get a formula in letter B for g of f of x. All right, let's go through it. Well, again, if I put x into f, what I end up having coming out is 3x minus 2. And then, if I want to know what g of 3x minus 2 is, take a look at g. G's rule is take the input and multiply it by 5. Here the input, though, is 3x minus 2. And then add 4 to it. So that's familiar, 15x minus 10. That's not so familiar. Plus 4. And that's going to be 15x minus 6. Notice these two formulas are not the same, and they rarely will be. Therefore, composition is not commutative. It matters which function comes first and which function comes second. All right, well, pause the video now and write down anything you need to. Okay, let's clear it out. Maybe do one more problem. Nice multiple choice. If f of x equals x squared and g of x is x minus 5, then what is f of g of x? Think about it a little bit. Well, this one's tricky on a variety of different levels, but you have all the math you need. Keep in mind that g of x is x minus 5. So f of g of x will be f of x minus 5. Now, what's f of x? It's take the input, which is x minus 5, and square it. Now, you gotta watch out on here, right? Multiplying two binomials can't be something that you know how to do on a Monday and then forget by a Tuesday, right? Very important. That should be a 5. Looks like a 6. So all I'm doing is multiplying out what they told me I would have to multiply out, right? They said x minus 5 squared. So I get x squared minus 10x plus 25. All right, a little tricky there. Easy to go with choice 1 or choice 2. All right, well, I'm going to clear out the text. It's gone. Let's finish up. So I think that the idea of function composition is pretty easy. An input goes in, output comes out, that output goes into another function, final output comes out. Pretty easy, but of course we can deal with it in terms of tables, graphs, equations. And then there's that tricky piece at the end, which we just started taking a look at, which was how do you do function composition and come out with a formula instead of just numerical values? More on that later. For now, I'd like to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.